Hello Q-steppers and fellow R coders, and welcome to another tutorial in the series of How to in R. This tutorial will cover how to compute bivariate linear regression in R and how to interpret those results. Again, we will use the most recent version of the Scottish Index of Multiple Deprivation released in 2020. We will use the income rate variable as the outcome variable in our models. This variable measures the percentage of people who are receiving welfare benefits and are therefore income deprived. So what is bivariate linear regression? In its most simplest terms, we are analysing if our predictor variable has an effect on our outcome variable. Remember that we cannot imply that X causes Y. It's simply how X affects Y. So how does it work? The goal of bivariate linear regression is to estimate the slope that minimises the residuals in the model. If you visualise a scatter plot with variables X and Y, so we have our data points, the regression creates a best fit line through the data that minimises the residuals. We can then make inferences on how much Y increases or decreases or stays the same as X increases. We can run bivariate linear regression as long as our outcome variable is numerical. Our predictor variables don't have to be numerical. You just have to take great care in the interpretation of categorical variables. Before we run bivariate linear regression in R, we need to create a subset that includes no missing values for the outcome variable. So we create a new dataset name for the global environment. We use the subset function. We name our original data set from the global environment. We then use the exclamation mark is.na function, then place our outcome variable in the brackets. So we see in our global environment, we have 6,973 observations. So to run the model, we give the model a name. We use the LM function, which is short for linear model. We then place our outcome variable, followed by the tilde sign, then our predictor variable, and we name our data. The predictor variable here is the employment rate variable, which is the percentage of people in a data zone that receive welfare benefits from the government as they cannot work due to long-term illness or disability. If we run this model, we will see the model name appear in the global environment. To view the results of the model, we need to use the summary function and place the model name in the brackets. Okay, so let's break this code down. The first line of output just reiterates the code that we've input above. Then we have a summary of the residuals. Remember, the residuals are the distance from the data points to the fitted slope. Ideally, this should not be far from symmetrical. So looking at the minimum and maximum values, then the first quartile and the third quartile, they should be roughly the same. And it's always good if the median is near zero. So then we have our coefficients. The coefficient shows the value for the intersect. This shows the value that if a data zone has zero employment deprivation, then the percentage of income deprivation should sit at around minus 0.16. However, we don't generally interpret the intercept or include it in results. We then have the slope or estimate for our predictor variable, which we will come back to in a second. The standard error and the t-value are provided here. This is what calculates our p-values. We aren't really interested in the p-value for the intercept, so we just checked the p-value for a predictor variable. It is under the 95% confidence level, so is therefore statistically significant. So the asterisks at the end also give you the p-value, so in line with the significant codes underneath. Here we have the residual standard error, which is the square root of the denominator in the equation. Then we have the degrees of freedom, which you will notice is the number of observations in the dataset minus 1. We then have our r squared and our adjusted r squared. With a score of 0.92, this is a good model. This means that employment rate explains 92% of the variance in the percentage of people who are income deprived. As we only have one predictor in our model, r squared and adjusted r squared will be the same. These will deviate when we add in more predictor variables if running multiple regression. At the bottom, we have the F-test results. This tests the model against the critical value, and if the r squared, or in other words, our model is significant. But I suppose let's just use this p-value provided. Usually this would be the first thing we would check when running a model. So yeah, we have a p-value under 0.05, so our model is significant. So let's go back to this slope for interpretation. The coefficient is 1.3, which is positive. We can therefore conclude that employment deprivation has an effect on income deprivation. We could further say, for a 1% increase in employment deprivation, we can expect income deprivation to increase by a percentage of 1.3. Let's run another example. Here we're analysing if the crime rate in a data zone has an effect on income deprivation. Okay, so we check this F statistic p-value. Our model is statistically significant. Our r squared is 0.11, so crime rate explains 11% of income deprivation. We then check a predictor p-value, which is under 0.05 confidence level. The estimate is 8.114 E minus 0.3. This means that we need to move the decimal place 3 times or add in 3 zeros at the beginning. We can therefore conclude that crime does have an effect of income deprivation in Scottish data zones. For a 1-point increase in crime rate, we can expect income deprivation to increase by 0.008, or you could say as crime rate increases in Scottish data zones, we can expect income deprivation to increase. However, the increase is really small. Let's run another model with a dummy variable. In this example, the predictor variable is the urban and rural classification of Scottish data zones. When interpreting a dummy variable in regression, we are analysing the effect of the higher value, which is urban data zones in this case. Now, if you've been following these tutorials, we transformed this variable into a dummy variable in the cleaning data tutorial. And this is the reason why. So we run the model, we check the F statistic p-value, we have a significant model. We check the R squares, which is very small in this case. We check the p-value for the predictor, and it's way under the 0.05 confidence level, so is therefore statistically significant. And the coefficient is 5.5. Okay, regarding interpretation, we can't really say urban data zones have an effect on income deprivation. That doesn't make sense. What we could say is that urban data zones are expected to have a 5.5% higher percentage of income deprivation than in rural data zones in Scotland. Hopefully this tutorial has got you familiar with bivariate linear regression and how to interpret those findings. So happy coding, QSTEPers, and remember to subscribe to our social media channels, and thank you for watching.